Thank you very much, and thanks for having me. Thanks everyone for inviting me. So I'll start with a couple of disclaimers. It talks to me a little bit disjointed, and I may be a little bit incoherent. I don't know if you saw this yesterday, 2 days ago actually. I never had an 8th of March. A plane was taking off out of San Francisco and lost a wheel. See right there? Well, I was on that plane. So I'm here safely, and I would really like to thank Akiko for what she did to get me here. And I feel good, but I don't know that that's really indicative of how we will perform. So but at least I'm here. Okay, so we started here talk. So this is the Institute of Sustainability, which is something I've been working on a lot. Chiral matters a little less, but there's a lot of things that we talk about when we talk about sustainability: decarbonization, hydrogen, renewables, lightweight materials, electrification, and so on and so forth. What people don't talk about is the fact that all of these interact with each other. Okay, so each proposed path, if we push it for it, makes other paths worse. For example, renewables are much more material in terms of technology than the way we harvest energy right now. So we want to go to renewables, but we have to make more materials. Same thing with lightweighting. If you lightweight and you displace steel with aluminum or carbon fibers, you're now looking at a material that has a much higher footprint than steel does. Industrial decarbonization, people say, oh, we're going to make green steel with hydrogen, green aluminum with hydrogen. Well, where is the hydrogen going to come out of? And that means we put more pressure on the fact that we already need to make hydrogen to make ammonia, and so forth and so on. And so it's a little bit like fighting a hydra. You think you're doing something to make one thing better, and something else comes up that makes things worse. And so the thesis today is calling a carbon shock. If we use carbon as a material, we actually can hit multiple of these issues at the same time and restore some of the balance that we disrupted on the Earth. So when I talk about using carbon as a material, what am I talking about? This is a plot by Ashby's book. Ashby's from Cambridge is the same of it. Ashby plots, of course. He got into looking at sustainability about 15 years ago, wrote a book that's on the 3rd edition. And this is a logarithmic scale, and over here, materials are just spaced arbitrarily. There's no scale here. So what you see is the first thing is you look at large scale, okay, let's say 10 million pounds a year and higher, which is this line over here. What you see is structural integrity is key to widespread use. You can't use powders in that big an amount. In fact, Ashby doesn't even have carbon black in this plot. I added it here. It's about 15 million tons a year, and it's not that much because it's used as a minority component, mostly to make tires for cars. The second thing that you see is there's a lot of materials that are being used here in low cost construction materials. It's going to be really hard to displace these materials with carbon because they are literally dirt cheap, because that dirt is what goes into concrete with cement to make concrete. But there is an opportunity over here. Okay, and it is, you can call these carbon materials. There are polymers, there's a little bit of hydrogen and something else. Primarily these are made out of carbon. There's another opportunity over here. I mean, it's interesting, an opportunity where carbon materials have not really been able to displace the incumbents, which is metals. They're high value. The cheapest steel is about 80 cents a kilo. Once you go to high-end steel and copper, you're at $70 a kilo, and then you go up here and they get more and more expensive. They're also used in transportation, where the fact that they have the high density is negative. They are responsible for a lot of what we call industrial CO2 emission. If you take copper, aluminum, and steel, it's about a third. Add cement, it's out of the industrial CO2 emissions. And there's another thing, which is it's not all about CO2. That's what a new aluminum mine looks like in the Amazon. Basically, it's a clear-cut forest. A river has been dammed to make hydroelectric power. And that's how aluminum is being made. And so when we talk about electrification and want to double the amount of copper, which is mined at 0.3% concentration in the ore, and we want to increase aluminum to make power transmission lines, and that's what we're looking at doing. So is there a better way to do that? And there is. I mean, there is basically what we could do is take hydrocarbons, split them. We do it with methane, which is harder to split. The energy works out that at least you need 4.7 megajoules per kilo of methane, but you get at least 35.5 megajoules per kilo of methane in terms of hydrogen, because at most, not at least, it's most you can get. And however, if you make the right type of carbon, you could then turn this into macroscopic materials. Materials have structural integrity on a large scale, right? And then put them in shapes and use their properties to go to a large scale. And there is one subclass of carbon materials that can actually do that now, and it's called carbon nanotubes. Okay, and I have samples on the first desk over here, so that if you want to look at them, you see what I'm talking about. Now, this is not a new material. There was a lot of excitement in the 90s, and what we call the large-scale production was obtained by the mid-90s, and the excitement was predicated, well, for physicists, the physicists got excited for other reasons that don't get me excited. But engineers got excited because of the properties. And people say, oh, this is stronger than steel, more conductive than copper. And of course, they all forgot that these are properties of continuous matter that were defined for continuous matter before the atomistic restriction of matter was accepted. And you can't really apply them to something that's only a nanometer or two in scale. In fact, we don't apply them to porous media the way they are. And so because it was very difficult to get these properties on the macro scale, and it was difficult even making macro scale material, there was a slump, and most people moved on and did something else. Now, the field has changed a lot. It's actually possible to make a macro scale materials, so fibers, tapes, etc., that are only comprised of carbon nanotubes. And production has gotten from lab scale to small industrial scale. Now, you know, I was talking about you need to make a difference at 10 million tons a year, but these are now materials that are made between 1 and 100 tons a year, which is halfway there, because it's on a logarithmic scale. To a gram to a ton is about as hard as a ton to a megaton. This is happening because we understand better how to make these materials. For example, there's very interesting processes. When you make these materials, you typically use tubular furnaces where you put in precursors for a catalyst, which are metal particles and gases that bring in your hydrocarbons. And you got two processes that are concurrent. One is that your catalyst precursor has to decompose and make the catalyst, and the carbon source has to decompose. If these two happen at the same time at the beginning of a reactor, you don't get growth because the carbon source is decomposing before the catalyst is ready, and you get soot formation. If this process is more rapid, you make the nanoparticles, and then your carbon source decomposes, and that's when you get the carbon nanotube growth. And the last is, if this process is too slow, your catalyst grows too large, and when the catalyst is too large, it no longer makes nanotubes, gets coated by soot and dies. And so there was no efficiency to this process, no attention to efficiencies. Reactors were treated as black boxes, but now we're finally understanding what happens. For example, in these reactors, what we understand now is there is a main flow where the reactants are injected on this side is actually vertical, and they're going down. But there is also a recirculating flow that brings the gases from the bottom to the top, and the gases on the bottom are hotter, and so these are actually bringing heat up in the front of the reactor. Injection has to be done deep into the reactor to avoid the recirculating zones and make the carbon nanotubes that you want. And what you see is that understanding what happens in the reactor brings productivity to much higher levels, and also the quality of nanotubes to much higher levels. Now, that material coming out of a reactor is still a structure. How do you get into fibers and tapes? And will you dilute liquid phase or fluid phase behavior? Now, this audience, I don't have to explain this, right? Rods will align and make liquid crystals at high concentration. We can skip this slide. It was known a long time ago. So first of all, does this stuff behave like rods? That wasn't clear back in 2000 when we started working on this. And so these are now carbon nanotubes that are being stained with a surfactant and are diffusing under Brownian motion. And sure enough, you measure the rotational diffusivity and you apply the classical theories for dilute rods and they work just fine. Now, if you go to higher concentration, what you see, to longer nanotubes, what you see is that they actually start fluctuating in shape like some effective stone chains would do. And you can actually back out the persistence strength by looking at the correlation length of a tangent. And you can then measure it. And you can also measure the diameter of each nanotube, not microscopically, but spectroscopically by taking the photoluminescence spectrum of each cube, which is uniquely correlated to the diameter. And you see that the stiffness of these molecules goes with the cube of the diameter as you would expect for an empty shell. And then what you find out is that sulfonic acids are solvents, and if you go to high enough concentration in sulfonic acid, you can make liquid crystals. And once you have liquid crystals, you can spin them much like the way you would spin Kevlar or other polymers and make fibers. You can also make foams by putting them into sort of shapes and removing the solvent, or you can make films. And so you can make materials. Lots of things happen that are not surprising is, now they're not surprising, is the transition from isotropic to liquid crystal goes with the aspect ratio, although it doesn't follow, it follows a parallel to the Gonzaga theory by about an order of magnitude lower because of the polydispersion of the nanotube, which is again something that is consistent with the theories for polydispersed rods. Now, when we started making fibers in 2004 with Rick Smalley, we were very excited with a paper in Science for this, but the properties were terrible. There's about 100 megapascal strength and about half a million Siemens per Siemens electrical conductivity. But then it turns out that by understanding processing, understanding phase behavior, and understanding the relationship between the properties of the nanotubes and the properties of the fibers, we were able to improve conductivity essentially double down in 3 years. And the samples got bigger and bigger. So I have some of these samples here, you have fibers, tapes, and fabrics. And some of these are, I guess, chiral because the fiber itself is not chiral, but when we make a yarn, we twist it and we will make a braid, it's not chiral again. So that's about as chiral as it's gonna get in this talk.
So it's a question about your beautiful tapes. What is the thickness?
So the thickness of the tapes is in the 10 to 40 microns. I think this is the 10 micron tape. Dr. Close, sorry.
And so you can, it consists of many.
Billions and billions of atoms. Yeah, of course.
Can you do something similar with graphene?
It doesn't hold us well. It's the reason why, if you think about the surface area per unit volume and the length. So these nanotubes that you have in your hands, the individual nanotubes are about 10 microns long, about 2 nanometers in diameter. So the surface area of the individual is massive. And they pack really well because of cylinders. Graphene, yes, you can, but typically what we see when we've done it is it's more fragile. Thank you. So here properties went up with time, and so now what you see here is this is strength divided by mass, which is a better measure of how good is a material, and these are electrical conductivity divided by mass. So you see, it's not the strongest material, it's not the most conductive material, but it's in the ballpark. So if one wanted to do material substitution, and substitute metals with these materials, you could do that now on the basis of properties. Now let me switch to boron nitride nanotubes because I know Ivan wanted to see this, so not only carbon. There's a stark difference between carbon nanotubes and boron nitride nanotubes. This is what they look like, they're white. Okay, again, for an engineer, this is like the first thing to notice. Now, structurally, they're the same as carbon nanotubes, except instead of having only carbon on the walls, they have alternating carbon and boron. Some engineers, especially NASA, really likes the fact that they don't burn as easily as carbon nanotubes. I wouldn't say that carbon nanotubes burn easily. You gotta take them to about 500 C and keep them there for a while. Boron nitride nanotubes will not burn until about 900 C. But the other thing that's interesting is that in terms of geometrically, they're about the same as carbon nanotubes. Again, this is all polydispersed, and depending on how you synthesize, you get different type of average and breadth of the distribution. But the diameter is in the few nanometers. The length is between a fraction of a micron to a few microns, maybe tens of microns sometimes. The big difference is band gap. The band gap is definitely puts me into the insulating region, and also gives this a white appearance, which also means that there's low visible light absorption. And I showed you some stuff about, there was an image of liquid crystals of nanotubes. It was done on very, very thin samples. When Ivan and I tried about 10 years ago to do anything a little more sophisticated than just optical imaging, we couldn't because the material absorbs. But this material is not going to absorb light as much. Now, it turns out that they behave similarly to carbon nanotubes when you put them in solution or suspension. Here is an experiment that's very similar to what I showed before with carbon nanotubes. These are boron nitride nanotubes have been stained with fluorescent surfactants. These are boron nitride nanotubes that have been dissolved in chlorosulfonic acid. These are cryo-TEM images from the Technion by Ishi Talman and his team, showing that all of these structures are individualized by the dissolution process. And so when you go to higher concentration, you start forming liquid crystals. What you see is the purity of your sample is critical. This is a lower purity sample. When it gets purified, what you see is a much larger liquid crystalline domains. Here, there's barely anything. But also what's interesting is that it looks like there's some sort of jelly structure or glassy structure, because you give it just a little sonication and these domains merge into much larger structures than their persistence. You can find tectoids in these regions, and then you can make films that, for example, are shear halides. Here you see as you rotate the polarizer and the analyzer, you see how the film has alignment, and you can also make fibers. Now, this is about as good as the carbon nanotubes were in 2004. So that's why there's no samples, because these are much more fragile and not something to take to a distinguished conference to brag about. Okay, but it's encouraging. We do think that there is something that we've never seen in carbon nanotubes, this kinetically trapped morphology. So this is a high concentration boron nitride nanotubes in chlorosulfonic acid. It's about 13% by volume. This is before sonication, and this is after a little bit of sonication when the material is already in the capillary. So you see much larger structure. You start seeing color, which you don't really see before sonication. And if you put it in front of an image, you see how the unsonicated solution has a lot of scattering, whereas the sonicated solution loses the scattering. We're looking at the phase behavior, and what we see, so these are the same images plotted as concentration versus thickness of capillaries, and these are thicknesses that are not really accessible with carbon nanotubes at high concentration. This is capillary thickness versus nematic thickness. So it's the same image, it's plotted in two different ways. So we see that typical dependence of color on the nematic thickness. At some point, it gets hard to fill the capillaries at high concentration. And the tactoids in a higher viscosity samples actually remain even after sonication, and that gives darker and unexpected biofrequency. But right now, this is also very exploratory. We can also do this in surfactants. Now, this is again purified boron nitride nanotubes in at 15%. This is with 5% surfactant. This is 15% surfactant. What you see is that at the lower concentration of surfactant, the type of surfactant you use seems to be very critical. At higher concentration of surfactant, the behavior seems to be a little bit more similar. Now, let me go back to the carbon. So I said, okay, we're going to make these carbon materials at a large scale. And how do you get there? Well, this is basically what you have to do. You have to start introducing them in high value applications and then keep reducing the cost of making it, which, you know, I'm not going to talk about how this is being done, but it is happening. And then progressively you go to applications that can tolerate only lower costs but have larger scale. And so over here, there are some things that these materials do that are kind of unusual. I want to call your attention because you may find some applications. So one, for example, is that you now have a conductor that is very flexible. And so you can put it through a sewing machine and put it on t-shirts, put it on rubber bands, and also has very low contact impedance with tissue. And so you can just put it on a t-shirt and pick up, for example, an electrocardiogram or the heartbeat if you just want the heartbeat. There's also some surprising things that come from the high surface area. This is NASA, who's made, this is not my work, it's work done by NASA with a company called Nanotubes, made pressure vessels for hydrogen storage. Normally, these are made with carbon fibers, so high strength carbon fibers. So you see these carbon nanotube fibers were about half of the tenacity and about a third of the strength of the carbon fibers. However, when they were put together in a composite to make the tank, they actually behave better. Another thing here is resistance to heat. That's a butane torch or propane torch. What you see is a stainless steel thread that resists for about half a second. Galvan CNT yarn. Now, Galvan is the trademark name of this material by one of the companies that makes it. Resists well over 30 seconds. If you do it against copper wire, copper resists a little longer than steel because it actually has higher thermal conductivity. It is about dissipating the heat away, but it's still talking about somewhere around 6 seconds, whereas the nanotube wire doesn't really promise. This is a cool one. Is there is a thread of carbon nanotube here, and now some guy is going to go throw an axe. And then you look at what happened. The axe has gone through the thread, and the thread has a nylon insulation. And see, it's gone through the wood, and the thread is not lost integrity. So cut the insulation, but not the thread. Some of this is being explained. This is work by Jae-Wang Lee at the University of Massachusetts, who shot micro bullets at one of these fibers and compared to aluminum, nylon, and Kevlar. Kevlar especially is known for being a ballistic fiber. And what he saw is when he looked at the ballistic behavior, the carbon nanotube fiber was better than Kevlar, even though on quasi-static pulling, in terms of strength, the rice carbon nanotube fiber is only about half of Kevlar. And the reason is that these fibers hold together by weak forces that are rate dependent, right? So when you pull them quasi-statically, you can actually pull them out more easily. When you hit them at very high speed, at some point, the dynamic friction is so high that you start breaking bonds. So in this case, we actually saw evidence of bond breaking in the impact structure. Similar work was done by, in this case, cutting by the group of Wenon Chen at Purdue. And again, interestingly, even though the Dexma fibers are not the strongest, they were the one that had the highest, the best behavior to cutting. It's also interesting work coming from high frequency wireless power systems. Is this is the group of Jong Park in South Korea, and what they saw is, again, even though the copper wires had higher conductivity than the carbon nanotube fibers, when they got to higher resistance, they got better behavior in transformance efficiencies. And part of it seemed to be also due to the thermal conductivity, which is very high. Another one was proximity effect. This is important for wireless charging. And the same group showed that carbon nanotube fibers have lower proximity effect. And so what I'm saying is a lot of the things that were anticipated in the 90s based on the properties of nanotubes are now coming back, and they're actually be present, although in lower form, in macroscopic structures that did not exist 20 years ago. So if this is something that's interesting, it'd be great to collaborate and see if this can be applicable in your areas. Now, the other thing that we're doing is because of trying to go to scale, we said, okay, we need to somehow organize this effort. We built something called the Carbon Hub at RISE. It is something that has three parts: a consortium where that funds and organizes research. There's an institute that essentially builds a community, and an accelerator that works at getting the work that's done by the institute out essentially in companies and something that's useful. And this is organized along the supply chains. Building markets are derivative supply chains. I learned this from economists in the last few years. And so if you try to develop a completely new material, you need to organize all the supply chain from feedstock all the way to intermediate goods, devices, and products and users. So we have companies in various parts of the supply chain that participate, and this is not only at Rice University, but we have university in multiple places that are all collaborating to work on this. And that has unlocked a significant additional funding from the Department of Energy, NSF, and most recently the Carnegie Foundation. So to sum up, I mostly talk about this part over here, and but there is a part here that one can talk about which is how do you build feedstocks for these carbon materials? Did you use fossil hydrocarbons, which is the easiest thing to do now, or did you go and use waste biomass or waste plastics through digesters? And if you do this, essentially you become carbon negative because you use waste biomass. You take carbon out with fixed by photosynthesis, you keep blocking from it. The other thing that you're going to do is you're going to make hydrogen, because there's hydrogen in all these feedstocks and there's no hydrogen over here, which also means that some of this hydrogen can be used to upgrade biomass, which is always one of the means of biomass upgrading. You often need hydrogen. Where are you going to get it from? There's other types of carbons that you can make that are granular, and they think were to be made much cheaper than carbon black. Carbon black is $1 to $2 a kilo. They would be able to be used as soil remediation, soil amendment, increasing use of soil and reducing use of water. Materials are electrically conductive, so we could build a vitrification. We could displace other materials and build our environment. Another thing is jobs and supply chains will be preserved here. Now, when you put this all together in terms of CO2, you see that you could have a 6 to 12 gigatons a year of CO2 impact on this. I'm going to thank my group. One thing I'm going to say is My group has been dwindling, so I'm looking for postdocs, if anybody has suggestions. And I'd like to thank my funding agencies, and thank all of you for my attention. I'm closing for 2 seconds.